Okay, Dr. Violette, what's the next case?
Well, as you recall, the last radiation problem we saw came from cables. You notice here, except for the power cord, cables are absent from this particular computer box because we are now looking at another avenue of radiation, which is through the apertures or the cracks inside the box or between the box and the frame of the computer, as in this case. In order to isolate these radiations that you see in a spectrum analyzer, we use this near-field sniffer probe. Now you observe what I do when I take this probe and I scan across the crack between the box and the case. If you look at the spectrum analyzer that we have over there, you notice how when I reach into this area right in here, how the emissions are up in amplitude, which means that essentially now the coupling from the signals inside to the outside world are essentially coming through the crack in this location in the backside of the computer. Now the next step will be to remove the cover, and then we will take a look at how we will fix this particular problem.
We'd like to remind you that for a formal test, the FCC requires what is referred to as an OATS, an open area test site. For the purposes of our demonstration today, we're doing everything inside, but normally the final test will be conducted outside. Diagnostics would be conducted in a lab just as we're doing it right here.
As we observe the high-level emissions that came from around the perimeter of the box, essentially these emissions came from an area right at the top of the box. Now the reason that we had high-level aperture-type emissions was the fact that if you observe the box has been painted with a non-conductive paint. And as a result, this non-conductive paint, although it made contact with the box, it still created non-electrical contact and therefore an aperture. Now a word about apertures. The length of the aperture is critical compared to the wavelength of the signal trying to come out. And if there's a signal inside that box at a frequency where the signal is approximately a half wavelength, which is the size of the aperture, that's when you get the maximum radiations through that aperture.
Obviously, that would not allow this piece of equipment to pass the FCC requirements. So what do we do to fix it?
To fix the problem that we observed before, we need to close the gap between the box and the computer frame. In order to do this, at the box level, at the package level, we did two things. Number one, you will note that we have removed some of that non-conductive paint. And then after we remove the paint, we put in a component called a spring finger stock gasket made out of beryllium copper. Now these gaskets are made by a company called Instrument Specialties in Delaware Water Gap, Pennsylvania. Now what happens here when we put the cover back on the box, we will have good contact between the spring finger stock and the frame and thereby close down that aperture.
Okay, let's put the cover back on the box and test it again.
Now that we have the cover back on, we notice that as we look at the spectrum analyzer, the high-level emissions that we saw coming from the crack between the box and the computer frame have significantly gone down. And also, if I use my near-field probe, my sniffer probe, where we saw some high-level emissions before, around this corner, you notice they have gone down considerably.
Yes.
What we have just done, Bill, we've observed the radiation from a cable on a digital computer. Now what we'd like to do is take a look at the source of this radiation. In order to do this, we have to move to another setup.
Okay.
The radiations that we just observed have a source or sources, and this is to illustrate one of these sources, which is the digital waveforms of our digital computer. On the lower instrument, which is an oscilloscope, where we measure amplitude versus time, we see roughly a digital waveform, which is a 50 megahertz frequency clock signal. And the rise time of that waveform is of the order of 5 or 6 nanoseconds. Now, when we talk about EMI, we usually talk about EMI in a frequency domain. So what we do is we take the same signal and we put it into a spectrum analyzer. which is the top instrument. Now, the spectrum analyzer provides amplitude versus frequency display. And what we see here are the frequency components of the digital periodic waveforms that we saw in the oscilloscope. Now, one thing to observe here is the fact that the frequency spectrum that we see in a spectrum analyzer goes from roughly 0 hertz to 1 gigahertz, which is a high frequency, and our attention focuses on the higher frequency spikes or components that we see here, because the higher the frequency, the higher the potential for radiation. And this accounts for the high frequency radiation, with the source being the digital waveforms in our computers.